Okay. So let's get started. Any question about anything before we move on? All right. So today I want to continue talking about control flow hazards and mainly what we define as branch prediction. So the last thing that we discussed last time was, so we talked about raw data hazards and forwarding and stalling and detecting the raw data hazards and all those things. And we kind of fix it. In most cases, we don't need to even stall the processor. In very rare cases, we had to stall the processor for one cycle and then move on if you had like a 5-stage pipeline. So we get a fairly decent performance out of this. Then we start talking about branches, and we said that the problem with the branches is that when we reach to a particular branch, given that there is a direction between, jumping left to the or taking the branch or not taking the branch, we don't know whether we can execute like fetch this instruction or whether we should for example fetch this instruction, given that the branch is not taken in this case and taken in this case. So if you think about our pipeline, essentially the problem was we had this pipeline of like 5 different stages. We put our branch here, the branch goes into the next stage of the pipeline, and of course something has to go inside, but we don't know really what is that instruction because we don't know whether the branch is taken or not. And we call this control flow hazard or control hazard. And we start thinking about, okay, how do we solve this? And the first thing was we can same as raw data hazards, we can stall the processors. And we talked about basically how many cycles do we need to stall the processors. We said that we need to think about 3 things in branches: whether the branch is taken or not, if it's taken, where does it jump to, and actually when do we know that this is indeed a branch instruction, because for all the other instructions we don't need to do anything. And the answer to those things was, at the end of the decode stage, obviously we know that this is a branch because our controller has decoded it. Take a look at it looked at the opcode and know that it's a branch. In finding the address of where to jump to, basically, which was the PC plus offset or was RS1 plus the immediate, was at the end of the execution stage or the beginning of the memory stage. If you look at like the way that we are computing it here, it basically was this point. And finally, whether or not this is a taken branch or not taken branch was kind of known at this point at the output of this AND gate, right? So these are the 3 things that I kind of like need to know. And if you combine these 3 things, it means that we need to kind of stall the processor for 3 cycles. With the design that we have, we need to stall the processor for 3 cycles whenever we have a branch. Whether it's taken or not taken, we don't care. We have to stall the processor for 3 cycles when we see a branch instruction. And I told you that on average for most of these applications that we write and use, 20% of our instructions are branch instructions. So in effect, that 20% of the time, the CPI for us is basically 4 cycles and not 1 cycle, right? So that means that our overall performance will take a hit. So it's just a weighted average of 20 times 4 plus 80%, 1. That's how much your CPI would be, right? So your performance definitely, decreases significantly. So we start talking about, okay, what should we do in order to make this better? And in this lecture, I'm going to talk about various things that we're going to do in order to kind of like reduce this overhead of branches. Maybe we can do some prediction, maybe we can like somehow reduce the stalls, all these things. So we're going to talk about all of these different tricks and techniques. And by the end of this, we will see that we actually can predict branches very, very effectively, about more than 90% of the time. And then also not only that, we can very, very effectively find where the branch is jumping to and know the address also very, very quickly. So both are kind of like what we call miss rate and miss penalty. Both of them decrease significantly with all these techniques that we're going to use and I'm going to describe in this lecture. Okay. So the first thing we start talking about was, okay, instead of like just blindly stalling the processor, what we can do and what we will do and we have used, a lot in our processor is some form of guessing. Are we good? Some form of guessing, or the more technical term for it is what we call speculation in processors, where essentially we don't know the outcome of a specific event. For example, in this case, we don't know whether our branch is taken or not taken, but we make a guess. We say that, oh, what if it's taken or what if it's not taken? And based off that guess, we start executing some other instructions. And if we are doing that guess, if we make that decision correctly most of the time, we will get a huge performance benefit because we essentially don't need to wait or to stall this the processor. And this is speculation things, as we also will start talking about out of order execution very soon. You will see that actually that is another place that we're going to use this guessing and this is speculation a lot. And you will see that it's the significant improvement in performance that we're getting these days from modern processors mainly actually is coming from this kind of simple but very effective technique of a speculation. Okay. So let's start with the not taken guess. So let's say that we are doing it very simply. For every single branch that is coming, we will say that it's going to be not taken. So still not the best guess that we can do. As we will see in future slides, you'll see that we actually can do it dynamically, sometimes taken and sometimes not taken. But let's start with not taken first and see what's happening with that. So we gave you this example in the previous lecture that if we have a branch that is not taken and if you have these other instructions, if we reach to this point that there is a branch and we need to, of course, fetch something, and say that, okay, this is a branch, and our current strategy is that we think that this branch is not taken, it means that we can safely, fetch all these instructions, right? So what we do is that we push the I1 here, the branch goes here, the I1 goes here, I2 comes in, and so on and so forth. So for not taken branches, if the branch is indeed not taken, we see zero performance hit because essentially we don't need to do anything. We don't need to be worried about anything, and so on and so forth, right? Any question at this point? Cool. And yeah, as I said, we don't need to stall at all. And I also gave you some stats of how accurate it is. We saw that basically, of course, the 80% of the time that there is no branch at all, we are good to go. For that 20%, we are 30% accurate on those 20%. So somewhere around 86% of the time for all the instructions, we're kind of we are good with our not taken branches. And of course, on that 14% of the time, we need to think about something else. And as you will see, that all we do from now on is improving this 86% up to ideally not 100%. Of course, we can never reach to 100% because reaching to 100% means that we know what's going to happen in future, which we don't know, right? So we're going to get close to 100% if you can. And that's the goal in our system. Okay. Before jumping into okay, how we can do it better, we also need to definitely talk about what would happen if we make an incorrect decision. Because again, as I said, in ideal scenario, we'll get to 100, but in realistic scenario, we never get to 100%. So there will be some scenarios, there will be some instruction, combination of instructions that we just made a mistake. We thought that this is not taken, but it's actually taken, or the other way around. So we need to think about what should we do. And this is a very serious problem because this is a correctness issue. Because, for example, imagine that you are writing your code with if some condition, and then do this, and else else do something else, and you're expecting, for example, your condition is true, so you're expecting that your branch is taken. So in your code, if you're debugging your code, you're expecting that these instruction gets executed, and these instructions are a skip. But if we actually make this problem here, if you don't fix this taken problem, what effectively hardware does is that it thinks that it's not going to be taken. So instead of running this part, it's going to run this part. So obviously the results and all the logic behind your code would be completely wrong. And this is a correctness issue that we definitely have to avoid. Yeah. So the question is this not taken is the standard across all the ISAs? So not taken is not a standard. We're just like going with the flow of like thinking about how to make this progressively more complex. So as we will see at the end of the day, what we will do in standard system is basically dynamically thinking about taken or not taken. So we will get there. But for now, let's start with a very simple branch predictor, because this is kind of a branch predictor in some sense. We're just always predicting not taken, right? Yes. Okay. So let's see what we should do with the taken case in this, or generally, what should we do when we make a mistake? And the solution for that is what we call flush, or in other words, we just have to get rid of all these instructions that are already in the pipeline and then go back and redo things in a correct way, right? So it's essentially the idea is that for example, we have a branch and we have I1, I2, I3, and so on and so forth. And maybe at some point there is a label, some instruction down here. And this is like T1, T2, or whatever, okay? So with the not taken scenario, we'll put so if we do fetch, decode, execute, memory, write back, what we will have is that we will have the branch, oops. So we will have the branch here, right? And then we will have the branch here, and then we will fetch I1, which we shouldn't have, but we do. Then we put the branch here, and then we put I1 here, and then we put I2 here. These are the cycles, right? So this is cycle number 1, this is cycle number 2, 3, and so on and so forth. And then at this point, if you remember, we told you that at this point here, at the end of this cycle, we know that we made a mistake, right? So we know that, oh, but we shouldn't have executed I1, I2, and I3. We should have, instead, we should have, executed T1, T2, and T3. So at this point, we say, oh, we made a mistake. So we will flush these instructions here with the method that I'm going to describe in the next slide. So we basically say, okay, whatever there is in these instructions here, we have to just ignore them altogether, and we need to, at this point, the branch goes into the write back stage, and the I1 and I2 and so on has to go to the fetch state, basically, right? So this would be T1, then T2, and so on and so forth. Okay, so we're basically saying that, oh, whatever we fetched and decode and execute, just get rid of all of them and just go back to, now that we have the correct address here, now actually go and start fetching the correct instruction. How do we do that? So remember when we were talking about the bubble instruction, and we said that the trick was basically we added this mux here, that basically all it does is that instead of sending the actual control signal, we send 0. And that's exactly what we're going to do for flushing instructions as well. So we're going to add this mux here and this mux here. And then we're going to add a mux, basically an OR gate here too. And what these thing does is basically saying that, you know what? So at this point, we are thinking, for example, so if, for example, this is our branch instruction, this will be our I1, and this will be our I2, and so on. So what we are saying is that, oh, at this point, we realize that we made a mistake. So instead of passing I1 control signals to the next stage, so it's actually going to go to the mem stage, we're going to replace this with this 0 thing, and we're going to send the 0 to the next. So we're basically saying that, okay, instead of sending I1, just cut I1 and then send bubble to the next instruction. Send all zeros to the next instruction. And we're going to repeat this from execute to memory, and from the decode to execution, and from the fetch to the decode. Okay, so for all of them, we basically need to do the same thing. We need to flush all of them and basically replace it with bubbles, with zeros. Okay, because those 3 instructions are incorrect instructions that's been fetched. So what we need to do is just replace them with bubbles. Okay, and then at this point we can then fetch a new instruction, a correct instruction based on the new PC, and then the PC will basically take care of the rest. So we're gonna execute T1, T2, T3, and so on. So okay. And interesting thing that you will see is that nothing bad happens in terms of permanent effect, right? So for example, I1 now is in the execution stage. So all I1 has done so far is reading RS1 and RS2 and immediate and so on, right? Nothing has been written permanently into our memory or our processor and so on and so forth, right? So that's why we are kind of like, in terms of like, just getting rid of the instruction, just replacing it with 0 is good enough. If, for example, we had already written to the register file, then we had lots of more problems because then we need to go and recover what we have written to the register file and all those things. And as you will see when we were talking about out of order execution, that's one of the problems that we need to deal with, because the time that we decide that we made a mistake, it's already too late. Things have been written in different places, so we need to actually go back and recover all those things. But for this specific case, things are good because we haven't written to our memory yet. We haven't written to our register file. So all we need to do is basically just clear our data path and replace our data path with zeros. Does that make sense? Anybody has any questions? Okay. So flushing basically means sending out, replacing those instructions and sending out with zeros. Okay. So as you can see, basically our hazard detection, again, similar to raw data hazard, our hazard detection unit is responsible for creating these zeros and sending those zeros out. And we are basically introducing this new control instructions called ID flush and EX flush. And we don't need a mem flush. Basically, all we need to do is just reusing EX flush for our mem flush as well. So that's why you'll see that basically this signal has been duplicated and being used here as well. Okay. So yeah, so what I can give you an example here. So our branch is here, then our branch goes here, our I1 goes here, branch goes here, I1 goes here, I2 goes here, branch goes here, I1, I2, I3. So at this point, we need to flush. So branch continues, of course, but instead of sending I1 here, we are sending 0 here. Instead of sending I2 here, we are sending 0 here. And instead of sending I3 here, we are sending I0 here. And at this point, we can actually start executing T1. T1 is the first instruction in our label, basically. And what happens here at this point, so this is done. The 0 goes here, 0 goes here, 0 goes here, T1 goes here. 0 is done, 0 goes here, 0 goes here, T1, 0, T1, T1, right? And then the rest I'm not showing here, but that would be T2, T3, and so on, so right? So all we did was basically just replacing things with zeros, and yeah, that's kind of like solve the problem for us. Okay. So we call this miss penalty because the penalty of making an incorrect decision is we need to kind of replace our instructions with 3 zeros. And basically what it says is when we are flushing 3 instructions, it's kind of as if that we are stalling the processor for those those 3 cycles. And it's slightly worse than that because not only we are kind of like flushing those instructions, but we are adding additional control to our data control hazard unit, and we also adding this muxes, and we also kind of like read some junks and did some wasteful activities. So our miss penalty in terms of performance only is 3 cycles, similar to the case that we were just stalling the processor and not predicting anything at all. But the real penalty that we are paying is that 3 cycles plus additional delays that we are kind of enduring because adding muxes and so on and so forth. Okay, so we call this miss penalty. The penalty that we need to pay for our miss speculation, for our misguessing. Okay, and still it's not a bad trade compared to the stalling, because at least in 30% of the time we are correct, right? So imagine that if we didn't do that not taken at all, for all the 100% branches, we were always stalling the processor. We were always paying that 3 cycle stalling. But with this not taken approach, at least 30% of those occasions, we are not stalling the processor. We are not paying the penalty. Okay. Still 70% we are paying that penalty. We improve basically our performance by about 30% or so. Okay. So that's one thing that we need to do. But again, as I said, the complexity that we are adding to the data path is something that we need to consider too. Okay. So far so good. We are talking about not taken, and we are talking about what will happen if we do taken. But let's actually now talk about what can we do instead of doing not taken. Can we do better than not taken or not? So there are multiple things that we can do. The first thing that we can do is that we are saying that, okay, let's stick with the not taken. But one thing that we can do is basically reducing our missed penalty. Remember, it takes 3 cycles for us to know that this indeed was taken. But for example, if we change this 3 to 2, or maybe 1, or even better 0, we at the moment we will know that we made a mistake, and we at least pay a little bit less penalty in terms of like flushing instructions. And that's a huge improvement, because 70% of the time, remember, for now we are paying that penalty, and if we reduce that penalty even by 1 cycle, we are improving our performance. Okay. So let's talk about how do we resolve the branch. By resolving means that we need to answer those 3 W questions, right? So we need to know whether, when, and where, kind of like, question. And we need to answer that. Okay. So ideally, what we want to do is being able to resolve the branch at the decode stage. Of course, we cannot resolve the branch at the fetch stage, because at fetch stage, we still don't know even this is a branch or not. What we know that when we know that this is a branch is at the decode stage. This is like, whether this is a branch equal, or if it's the other instructions. But we are basically wasting 2 other cycles in the execute and mem, because we need to know what is the address and whether this branch is taken or not. So what we are proposing is we need to move this where and whether to the decode stage, ideally. And if we move this ideally to the decode stage, we are only paying 1 cycle penalty, right? So instead of 3 cycles, we are exchanging this with 1 cycle. So let's see what we should do with the where and whether parts. Remember, the where part was the part where we get the PC and add it with our immediate, right? So we need to basically, all we need to do is that we need to move the next PC calculation into the decode stage. So basically that adder and that multiplexer and all those things, if we move it to our decode stage, then we kind of like solve this problem. Okay. So that's one thing we need to do. So the interesting thing is that the whether part can also technically be resolved in the decode stage. Why? Because if you remember, our branch instructions are essentially some comparison between RS1 and RS2, right? So for example, for equal, it was like whether this, for less than was this, for greater than was this, and so on. So we usually basically what we need to do is that if we have RS1 and if we have RS2, which we actually have in our decode stage, all we need to do is applying that, comparison, whatever that is, whether it's equal or less than or whatever. And if you do that during the decode stage, we're basically solving the whether problem as well. Okay, so this basically would be our data path based on these 2 assumptions. As you will see, this part, which was basically PC plus offset, was originally here, and now I moved it here. And then all those things about the branch and whether it's going to be taken or not, it was here, right? So there was this AND gate here, and then the AND gate was basically going here. Instead of all those things, I'm just removing all those together, and I'm adding this comparator, which symbolically I show it as equal, but in reality, this is a fairly complex comparator, which can, compare equality, can compare less than and greater than and whatever else that we have in our branch predictor. And as you can see, basically being fed by RS1 and RS2. And we didn't show the control signals, but in reality, there is a control signal also coming to our comparator here. Okay, so this is technically part of our controller in some sense. All we need to do is feeding RS1 and RS2 to our controller, and the controller basically takes care of this. Okay, so this would be basically our whether or not this has to be taken. And then once we have that, then the controller can basically send this control signal to our mux here, right? So this is the mux that decide whether we have to do PC plus 4 or PC plus offset. So what we're suggesting is feed RS1 and RS2 here, add this comparator to your controller, and then now your controller can basically just issue one multiplexer signal here, and that would be deciding whether we are doing PC or PC plus offset. Okay, and then the PC plus offset value is basically coming from this side from here, right? So we are adding this additional signal to our system as well. Okay, is that clear what we're doing this? Yeah. So the question is, where does the output of this comparator comes from? So I think so I took this from the book, but unfortunately, I think there are some things that are missing in this picture. So what this should be, it's basically, think about this as blue as a control, and it's in reality is not implemented here, it's actually implemented here. And in that case, the outcome is basically coming from the controller, and the outcome is this control signal that goes into this multiplex. Does that make sense? Yeah. So yeah, the question is that equal is only for branch. Yeah, as I said, this is in reality a comparator, which could be less than, greater than, all those things. I'm just using this to kind of like, symbolically show that this is a comparator. Again, something that might have been better if you show it differently, saying comparator rather than equality. So the question is that now the register needs to be routed to the control list. Yeah. Only RS1 and RS2. So the question is that for this, we no longer needs flush signals at EX and memory. We still do, because there might be cases that we fetch one instruction incorrectly, because we still at the decode stage we know this, and there is already like I1 in our fetch, so we need to kind of like flush I1. But yeah, for the rest of these instructions, we don't need to flush it. And then another thing is that the reason that we have these is because we will need this in future for other things that we will discuss. So that's why we're keeping this. In reality, for this specific case, you might not need this at all. Yes, that's a good observation. Okay. So yeah, so these are the things that we are doing. Still, as I just said, we need the IF flush because there is I1 that we need to flush. So we basically, what we do is that if you're reading I1 here, we need to get rid of I1 and then just send 0 to the next instruction. But other than that, we are kind of good to go. Okay. So as you can see here, what happens again, back to the similar example that we had before, this time we will have branch equal, for example, here, then the branch equal goes here, our I1 goes here. And the nice thing is that at this point, we know that we are making a mistake or not making a mistake. So our branch equal goes forward. If the branch has to be taken, then we need to basically, instead of sending this, we will sending 0 here. So 0 goes here. At this point, we can safely then fetch T1 here. Branch equal goes here. 0 goes here. T1, T2, and the rest of the story. Branch equal 0, T1, T2, T3, and so on and so forth. right? So as you can see, the difference between these two is that we, instead of having 3 zeros, we are now only having 1 0. So we are trading 3 cycles of miss penalty with 1 cycle of miss penalty. The reason that it's still paying that 1 cycle is the branch is being resolved in the decode stage, right? If we manage to actually resolve the branch in the fetch state, which we're going to talk about, then we don't even need to, like, pay this one cycle penalty as well. Does that make sense? Okay. The interesting things before jumping into the next part is that there's a little bit of housekeeping that we need to kind of, like, figure out. And that is that when we are reading RS1 and RS2, unfortunately, we get the same data hazard problem that we had before, because remember, our data hazard was we were forwarding things at this stage, right? So if you go back to our raw data hazard, we were saying that at this point we are reading garbage, right? And this garbage will go here, and we are adding these 2 muxes here, which basically was what we call forwarding muxes, right? And we were kind of correcting that decision at this point, right? So in the middle of the EX stage, that's where we were kind of like fixing our raw data hazard problem. But what we are suggesting here is that if you're reading these 2 instructions here, and we were writing to the same, for example, RD and RS1 are the same thing. So in the same cycle, RS1 is being written, then we will have the exact same problem that we discussed last lecture about the raw data hazard, in this case here. And the reason, again, that this raw data hazard is coming back to us is that the timing is off, because in our original forwarding, we were fixing the issue in the execution stage, but now we are suggesting to read RS1 and use RS1 in the decode stage, okay? So what should we do? We basically need to do the same trick that we use for our EX stage. We need to add this additional multiplexers, which basically gets their value from, from the forwardings of, what is this? And this one is, I think, here. So we basically saying that, add this multiplexer. This one is coming from the register file, and this one is coming from the later stages, right? So this is our original RS1, and this is the forwarded RS1. And here we need to issue another control signals from the forwarding unit to basically do the forwarding for us. So what we're doing here again is we're fixing the raw data hazard, this time at the decode stage compared to what we did before in the execution stage. The reason for that is we want to use RS1 and RS2 during the decode stage for resolving the branch sooner. And so all we need to do is adding additional multiplexer to our forwarding units to kind of fix that issue. So the rationale and the way that we are doing it is exactly the same as what we did before for our execution stage, but this time we are forwarding it back to the decode stage. Okay, does that make sense? Any questions? Okay, so forwarding conditions would be very, very similar to what we showed before. You need to compare RS1 with RD and RS2 with RD. You also need to check whether this is indeed read-write and nothing else. But one thing to pay attention to is that this one is IFID instead of IDEX. If you look back at your original raw data hazard, this was IDEX, but this time it's IFID, which means that we are basically forwarding it back to our decode stage rather than forwarding it back to our execution stage. Okay, is that clear what we're doing, why we're doing this, and what we're doing exactly? Excellent. And then you might ask what will happen for load use. Because for load use, remember, we didn't know what is happening during our execution, and we only know it during the mem stage. Again, same story that we said there applies to here. For load use, unfortunately, forwarding alone doesn't help, so we need to stall for one cycle and then forward in the next cycle. Okay, so if we have a branch that it has a raw data hazard with load use, we need to stall for one additional cycle and then forward. So remember, if it didn't do anything, we had 3 cycles. If we do the correct forwarding and moving everything to the decode stage, we have 1. And if you have load use data hazard coupled with your branch, then you have basically 2. Okay, because you need to stall for 1 cycle and then you do that additional cycle. Okay, so it's kind of like, a little bit complex, unfortunately, but you have to kind of like, there are different cases, corner cases that you need to think about. Okay, is that clear why we're doing this? Great. So kind of like, very quickly to talk about what we have discussed so far, kind of like, taking a step back. So we are trying to reduce our miss penalty. So we're still doing not taken, and by not taken, we are improving our performance from 0 to 30%, right? And by moving the 3W question, basically we are reducing our miss penalty from 3 cycles to 1 cycle. Of course, there will be hazards, so we need to add forwarding. For regular raw data hazard, we can fix it by just adding those 2 muxes to the output of a register file. It just means that, again, our data path becomes a little bit more complex. And as you can see, the trend that we started this innocent looking, single cycle and start adding things to it more and more. And you see that how we are actually from like, million transistors, we are now at billion transistors, and our processors gets more and more complex because of these decisions that we're making. But the nice thing about this is that now we are reducing our miss penalty from 3 cycles to 1 cycle. And if we have the load use data hazard, then we have to stall for 1 additional cycle. So we kind of like reducing the miss penalty from 3 cycles back to 2 cycles. Okay? Great. So before jumping into what we can do even better, let's actually also very briefly talk about the role of the compiler here. So we not, as you can see so far, we haven't talked much about the compiler. I recommend you, if you are interested in kind of like interaction between the system and hardware, read more about the compiler. We're not going to cover much, but 3 things that the compiler can do to help us, basically reducing this 1 cycle miss penalty is, so remember when we have a branch instruction and I1 instruction, I2 instructions, so on, and then somewhere label here and T1 instruction here. We said that basically if we move things to the decode stage, we still need to pay 1 cycle penalty if you make an incorrect decision. Okay. So one trick that we can do is if at some point here there is an instruction, so basically we have an if, maybe using a different color. We have an if instruction. Basically, these are if, and this part is the else, right? And at some point here, maybe call it M1, is actually when the else condition also ends, right? And this is basically regardless of whether we are taking the if or else branch, at some point, both of them kind of converge to M1. So what we can do is that if the compiler can find this M1, can push this M1 here, of course, if there is no dependency, or any other instruction that's kind of like independent from the rest of these instructions. By independent, I mean that the sources that it uses doesn't been written to by any of these instructions here. Then we kind of like completely solve the problem of branches, because even if there is a misprediction here, we don't need to flush anything because M1 is a legitimate instruction anyway. Whether this branch is taken or not taken, we don't need to flush M1 because M1 has to be executed some point in future anyway. So the nice thing about this is that we basically effectively reducing our miss penalty to 0. And that's what we want. But the challenge is 2 things. One is compiler needs to find this instruction, and finding this instruction is not trivial. So our compiler gets more and more complex. And the second thing is that we kind of need some additional circuitry in order to kind of like, understand this because our PC is kind of like, jumping somewhere else. So we need to kind of like add a little bit of circuitry into our system as well. Question. The question is this the idea of out of order execution? In some sense, this is an out of order execution, but it's compiler directed out of order execution. As you will see in the out of order execution, compiler doesn't do anything. The hardware itself kind of figure out these things. And as you will see, that's where we're going to reach to eventually, that we don't need the compiler to tell us which instruction should go where. We will develop a mechanism in hardware that can actually go and search through all these instructions. Okay, so that's number one. So we call this delay slot. This slot after the branch is called delay slot because basically if we can delay all the instructions by one, then we kind of solve the issue of flushing. And if we can fill this delay slot with an instruction that doesn't need to be flushed, then we kind of like, improve our performance, right? So we can do this delay slide. And in fact, in many compilers, this is one thing that's being done. But it's not guaranteed that we can always find this instruction. So it doesn't mean that we're effectively reducing our performance. Reducing our miss penalty to 0. Sometimes we can find this. Sometimes we cannot find this, okay? Another thing that we can do is that if we are going with this not taken story, what the branch can do is reorder things for us such that the chance of not taken becomes much, much more higher than the chance of taken. Remember, we told you that 70% of the time you're doing taken and 30% of the time you're doing not taken. If the compiler reorder the if then else's in some sense, we can actually do the opposite, right? So we can do not taken more often. Another thing that the compiler does is what's called loop unrolling. So the loop unrolling idea is that we can basically get rid of our branches, especially for loops, right? Because loops are these backward jumps that is very inaccurate and always taken. So for example, if you have 4 and then list of instructions here, and then you do this for maybe 10 times. So you always have this, and then at the end of this, you have a branch that's kind of like jump to the top, right? So what you can do is that if I unroll this instruction, basically I repeat this instruction 10 times, this list of instructions 10 times, then I don't need to have any branch at all. I just run the first block, then run the same block again and again and again. How many iterations that we have? And this means that, I don't even need to be worried about the branch. So our performance significantly improves. Questions? So the question is, if you're writing your program, you can't do this. You can if you know what is the trip count of your loop, right? So the question is, do we have to do it ourselves, or is this a compiler's job to do? Both. So as a software developer, you can think about this and actually unroll your loops if you can. But it's a very standard thing for compiler to unroll your loops. So yeah. So the question is, how do you increase the chance of not taking? So there will be scenarios like this that, so if I go way back, okay, here. So we have this and this, right? We have the true and false. And we said that we basically need to linearize this. If I know that, for example, this branch is not take, if you want to really have not taken, what I can do is that I can play with where I place C and B, and knowing that which one is more likely, and then I put that into the top. So basically, compiler needs to kind of profile the code before, and based off that, kind of like make a decision that where to put B and where to put C. Does that make sense? The problem with going back to the loop unrolling thing, the problem with the loop unrolling though is one thing that is obvious. Anybody can point out what would be the problem with loop unrolling? Memory. So yeah, so the answer is more memory, because we are essentially saying that, oh, we had this some instructions, some static number of instructions, let's say 10 instructions, and then we had a branch. So in terms of actual number of instructions in our instruction memory, we are only occupying, for example, 11 instructions. But if I want to unroll this, I basically say that whatever this number of instruction is, for example, this is 10, and if I need to iterate this 10 times, I'm essentially changing 11 to 100, right? Why 100? Because I unroll this loop 100 times, 10 times, so I get 100 instructions. So the amount of, memory, instruction memory that we are occupying with loop unrolling is, for example, it's basically order of whatever your iteration is. For example, in this case, 10. So basically, whatever that number of iteration times the number of instructions, right? So loop unrolling for smaller loops, good and possible. But for if you do this 1,000 times, you cannot unroll your loop 1,000 times because that will essentially, takes the entire memory, right? So that's something you need to think about. Like basically the change between the kind of the trade-off between your dynamic instructions. In both cases, the number of instructions you're executing is the same, but the size of your code, which we refer to static size of your code, significantly grows if you do that loop unroll. So the question is, what if it's a while loop? So not all the loops can be unrolled, right? So if you know your trip count, and if you can do that, if you know there is multiple times that this will happen, then yes. But you cannot eliminate your branches altogether. There is a completely different train of thoughts, which we usually call it oblivious programming, which essentially say that, oh, get rid of all your control flow altogether, write a program that doesn't have any loop at all. But that requires algorithmic level changes. So you basically needs to change your algorithm completely that doesn't have any loop. And it's not something that you can do all the time. So it's not what we call Turing complete, because there are some algorithms that do need some branches. So for example, I think for your homework, there were people coming up with this designs that doesn't have any branches, and other people coming up with designs that had branches. That's a very good example of a scenarios like this. If you can come up with algorithm that doesn't need loop unrolling, or the loops is kind of has no number of iterations, then you're good to go. Mm-hmm. But so the question is that if you have a loop with 10 iterations, why don't you change that branch to a jump 9 times? But again, how do you know that this is not 9 times? You need some form of counter somewhere that tells you this is 9. So you either have to unroll it 9 times, or you need some form of branch that tells you this is 9. Then don't do it, right? So it still will be a branch. Okay. So going back to our hardware, so this is kind of the very quick thing about the compiler. Going back to the hardware, we basically, by saying that we are resolving the branch sooner, we are reducing what we call the miss penalty. Okay, but still we are only doing 30% on our miss rate, right? We are, by doing not taken, we are only doing 30% on our miss rate. So that's not great. So let's see actually what can we do better, right? Can we maybe improve this 30% to something better? And the quick answer is, what if we, instead of doing always not taken, we do always taken? That immediately moves us from 30% to 70%, right? So we are doing the exact opposite, and immediately we get more than two times improvement in our performance, right? So that seems to be a good strategy. But think about taken. What do we need for our taken branch, right? So doing taken, unfortunately, is not trivial. Anybody can comment of changing from not taken to taken, what we need to do? So one thing is that we need the offset for the branch. Yes. So we need the where part, right? Any other potential problem? we need to know that this is actually indeed a branch, because if you're saying taken, we need to say that this is a branch and then we have to take it, right? Because remember, for the not taken, we don't need to be worried about branch or other like R-type or SW or memory instructions, right? Because for all of them it's not taken. So for all of those scenarios, PC is always PC plus 4. So we're good, right? But immediately after changing this not taken to taken, then not only we need the address, as you said, but we also need to know this is indeed a branch instruction, and then fixing this issue. Because for all these, we always say that we don't care what this instruction is. It's always PC plus 4. But now with this, we need to also say, oh, we know that this is branch. So PC is not PC plus 4, it's PC plus something else. Okay. So we need these two problems. So the first thing, as you said, is that we need to basically find the next PC or PC plus offset, in other words, but this time at the fetch state, right? Because if you want to predict things that are taken, we need to know it at the fetch state. Basically, if you think about this, is that fetch, decode, execute, memory, write back. So our branch goes into here. And remember, we want to say that we want to predict that this is taken. So basically what we want to fetch at the next stage is we want our, let me do it the other way. So this is our branch. We have our branch at the fetch state. Then our branch goes to the decode stage, right? At the second cycle. So this is first cycle, this is second cycle. And we have our I1 here. And then at some point we have our T1 here, right? And remember, we want to say that, oh, this is a taken branch. So what we want to do in this cycle here is T1, right? So how do we get T1 at this point? We need to know what is next PC at the end of this cycle, right? And we don't have that information. We have that information by these tricks that we did. We have this information at this point here. So we need to somehow even move our next PC computation back to the fetch state. Okay. Anybody has any doubts why we're doing this? Okay. So we need our next PC at the fetch state. So let's see how we actually do that. So the trick for this is that we don't have that information in our fetch states. There's no way that we can do that, unfortunately, unless we move our controller, we move our register file and everything to our fetch state, which effectively what we are saying is that we are moving back to our single cycle design. So we cannot do that. We cannot move our RS1 and RS2 reads because that's the register file part. We cannot move our controller to fetch states. That's also part of your decode. So you cannot move those things similar to the way that we move things from the execution and memory stage to our decode stage. So what we are doing is that we're going to use this table to kind of keep track of things that we did in the past. And we're going to use this idea that, okay, for the first time, maybe we cannot do this, but the second time that we will see this, we can use this because this is the same address that we have seen before. So maybe we can reuse that address. Okay. So we basically what we're trying to do is that we are trying to guess the next address or next PC using this kind of like table that I'm going to describe in the next few slides. So again, the idea is that if we see a branch instruction for the first time, it will at some point it will jump to next piece to T, right? So if I have this branch, let's say for now we cannot do the taken, so we make some mistakes, but at some point in our pipeline we will see that it's jumping to T1, right? So we know this address now. What we are proposing is that the next time, not this time, the next time that we will see the same branch, we know for sure that this branch, if it's taken, is going to jump into T1. So what we will do is that we're going to remember this, and we're going to remember this branch and T1. And I'm going to say that next time I see you, I know that you're going to jump to T1. So I know my address, right? So basically our guessing is kind of like, a memory in some sense that we are adding to our fetch state, and we are saying that, okay, next time I see this, I'll know where it jumps. And you might quickly ask, okay, why would that be helpful? How it only will be helpful if we see these branches and these other branches multiple times. Effectively, what I'm saying is, if you're seeing your branches more than once in your program, most of your branches at least, then this method works really well, right? And another thing that you might ask is this always correct? Because I said that your branch always jumps to T1. Is this a correct assumption? In most cases, yes. Only in cases that we have something like JALR, which is R1 plus the offset, that's the problem that we're going to have with this approach, which later on in the lecture, I'm going to talk about that. But for most cases like branch equal or for GL, which are direct jumps, this is actually a correct assumption about our next address. So wherever I see branch, I know that's going to be T1. So I'm going to record T1 and I'm going to see it again, hopefully. And then if I see it again, I know that the address is T1. And the nice thing is that I can do this in fetch stage because I can just put a memory in the fetch stage and kind of solve the problem, right? And then the first question is how frequent this is. If you think about all your for loops and while loops, and generally any of those loops that you have in your program, all of them happens more than once. So the first time you pay the penalty, from now on, if you run it 1,000 times, all the 1,999 times, you know the address. So we kind of effectively, for those loops that iterate more than a few times, you get a huge performance benefit with this idea. Does that make sense? Any questions? Yeah.
Branch is going to go to a certain place in the fetch stage if you're using the fetch stage to determine that it's a branch.
So the question is, how do you know that where you jump to in the fetch state without basically determining that this is a branch? Actually, great point, and that's the main challenge that we're going to resolve in the next few slides. So that's the main thing. You are in the right direction. The idea, though, is we want to, if we know that this is a branch, this method will work, right? So that's the idea. But I'm going to get to the details. Any other questions? Okay. So this is the idea of what we call branch target buffer, or BTB. So the BTB, what it does is stores, think about this as this array or this memory, small memory that we put in our fetch state that has these lines. And these lines are basically recording the PC and the target address. Why are we storing PC? Anybody? So the answer is different, because remember I said in the previous one that we know that this is branch something, and then this is the address to that branch. Each branch has its own target address, right? So you need to know which branch this is, and what's the best way to know what branch this is? Basically, each branch has its own unique PC, right? So or address, in other words. So our PC, which is basically pointing to the address of this branch, tells us what is the address of this branch. So we can actually record that address, and it says that this is unique to this branch. So we basically, the identifier, the distinguished factor between this branch and that branch, because their opcode are exactly the same, their offset might be exactly the same, and all those things. The only thing that differentiates different branches from each other is their address. And their address is known by knowing the PC, okay? So if we know the PC and we kind of like record the PC with the target address in each of these lines, then we're good to go. We are basically can say that this is this branch and this is their target address, and we never make a mistake, okay? And another question would be, okay, how many bits of PC are we going to record? And that depends on how many entries do we have here. Same story with our inst mem. If you recall, we said that essentially if we have this such and such number of rows, log2 of that would be the bits that we need to address this memory. Same story for here. So if you, for example, have 8 entries, you need only 3 bits, right? So you need 3 bits to index this, and you technically just need 3 bits to kind of like save things in your, so lower 3 bits of your PC, for example, would be enough, right? So how many bits do we need that here is basically depending on how many entries you will have in your BTB. I'm going to get back to this later on, but for now, just assume that you have an unlimited table of entries. In each entry, you're saving the whole PC maybe and the target address for that. Okay, and that's the definition of what we call BTB, or branch target buffer. Okay, it's a buffer, it's a memory that just saves or remembers the branch targets, the address that we're going to jump into. Okay. Let's pause here, and then I'm going to go back and then now start talking about BTBs. There are lots of things that we need to talk about BTB. Okay. Yeah.
So, okay, the lookup table in parallel while we.
So the question is, do we do it in parallel with the branch? Yes. We do that. Yeah. So while you're fetching the instruction, you're also fetching from your BTB. Yeah. I'm going to get to that. Okay. So we now know that we need branch target buffers. So let's actually go through the details of our branch target buffer. Okay. So basically for our BTB, we are following this 2-step simple algorithm. For a new PC, for a PC that we haven't seen before, for a branch that we haven't seen before, we record the target address into our table. Okay. So that's one thing we do. For every new branch that we haven't seen before, we just need to put a new entry into our table. Later on, we're going to talk about like how do we do it for the first time and so on. But the majority of scenarios is when we are seeing an recurring PC, a PC that we have seen before, and we need to look up the table. We basically need to go through the table, which I'm going to describe how we do it. And then find, in other words, predict the target address, and we need to basically replace the current PC plus 4 with that PC, because we have recorded that target address. We have recorded that address. We need to replace the PC plus 4 with that address, right? So basically, if I want to show this to you graphically, we have our PC here. This is our BTB, which essentially, again, it's a memory. It's an array very similar to our instruction memory. Typically, this array here is much smaller than our instruction memory, because we don't need to. The number of branches, of course, is much less than our total number of instructions. But all it does is basically use this PC as the index in order to go through here. We're going to talk about how do we actually find that PC. But let's imagine that we find that, and that would be our next PC in some sense. And that next PC is basically goes into a mux that has PC plus 4 and has that target address. And that would be our next PC, right? So this way we kind of like, know that this is our address, okay? And then the whole thing about the instruction and how the instruction works and so on stays exactly the same as before. And remember, all these things are happening in our fetch state, okay? Question? So the question is that this design benefits for loops and not if else. Yes. So if you see branch only one time, then this probably won't work. But if you see a branch for multiple times, yes, then this works. So the question is how much in general this can save the CPU time? A lot. because most of the branches that we see are kind of like, branches that's always taken or always not taken. What you're suggesting is for those branches that we don't know sometimes are taken or not taken or only happens once. Most of the branches happens multiple times because there is this rule that 90% of the time of your execution time only it happens in 10% of your code, which means that you typically write so many lines of code, but 90% of your execution time on average only happens at 10% of that line of code. But usually it's some form of a while loop or for loop or something like that, or a function that's being called over and over again. So it's usually you have a what we call a hot region in your code that you spend a lot of time there, and this helps to improve the performance of that. So yeah, it's huge. Uh-huh. So the question is that if the instruction is not in the BTB, if it's not in the BTB, this PC will be a garbage. So it will be some value that is garbage. So this next PC. And we need to kind of like figure out here. So basically we're not doing the taken part, we're doing the not taken. Or worst case scenario, if we make a mistake, we will realize that if this was not taken and we need to go back. Does that make sense? But I'll actually talk about what goes inside this and whether we might have made a mistake or not. We'll actually get to that point. Yeah. So where this coming from, right? Once I describe this, you will see where this coming.
Does the BTB also store whether or not the branch was taken?
So the question is, does BTB decide also, say whether or not this branch is taken? We will talk about the dynamic. So for now, we are only focusing on taken branches. So we always predict that it's taken. So if it's a branch, it's going to be taken. Okay. So two very important questions. One was asked before, and the other one was kind of related to what you said. The first is, how do we know that this is a branch? Like basically, how do we know that this value should be equal to 1 in some sense? Because if this is equal to 1, we're kind of like jumping. And another thing is, how do we put things into our BTB? Like who is responsible for updating our BTB? And how do we put that address in our BTB, right? Let me actually answer this first, and then I'm going to jump into, because this is kind of related to that one. So who puts who updates the BTB is basically our processor. We're not going to show kind of the back channel to our BTB, but once the instruction is decoded, remember that we're still doing the same things of answering all those 3 W questions in the decode stage. So once the instruction is decoded at the decode stage, we know that whether this branch is taken or not, we know the target address, and we know that this is indeed a branch instructions. So that means that during the decode stage, it's a great time to update our BTB. Basically, we know that this is a branch and this is a taken branch. So we have to go to our BTB and update that address or create that new entry into our BTB. Okay? Question.
So does the update process only happen during the first time the branch instruction is called, or every time?
So the question is, does this happen for every time or does happens for one time? For direct jumps, only needs to happen once, because all the branch always jumps into the same address over and over again. If this was an indirect jump, for example, RS1, if this was a GLR, then we need to like update it over and over. For now, we are only talking about branch type instructions and JAL instructions, so only happens once. Okay. Mm-hmm. So the question is that we said that the BTB is indexed by PC, so there won't be a lot of gaps between what? Yeah, there won't. We will actually talk about how do we cleverly pick our indexing methodology in the next few slides, actually. Okay, So kind of like who updates the PC, who updates the BTB, the processor updates the BTB. We're not going to show you the circuitry for it, but imagine that there will be a wire goes back into our BTB with the write and write enable and all those things. And we only update our BTB if this is a branch and if this is a taken branch. So if it's not a taken branch, we're not going to go to the BTB and update that. Okay. So just remember, if this is a taken branch, we're going to go and update our PC, our BTB. Now, how do we know that this is a control flow instructions? The nice thing about that is because of this, if that PC match with one of our entries in that table, it is guaranteed that this is a control flow instruction. Why? Because we are saying that whatever exists in that table only coming from the fact that this was a taken branch coming from our decoder. So if it's there, it's guaranteed that it's a taken branch. If it's not there, we don't know, and we're going to do not taken. So the trick that we're going to use is this, that we check our table. If it's there, it's guaranteed that this is a taken branch. We know this is a control flow instruction. We take the PC and use it. If it's not there, then we say that we don't know. It could be a branch instruction. It could be taken. It may not be taken. So what we're going to do is that we're going to just ignore, continue, pay that one penalty of not taken, and then go back and say, okay, did we make a mistake or not? And then the BTB will update that. So the next time we see the same instruction again, we know that this is again a branch and we're good to go. Question?
So it's we save both. So if we use the current the table, would that not with the last PC, but nothing.
Say it again.
Actually, I don't. I think
You're good. Yeah. So what you store is PC. Even if you have PC plus 4, you can just deduct it with 4 and then take it, right? So that's not a big deal. And you still have that wire of PC somewhere. You can just connect that wire to your BTB, right? Any other questions? Okay. So kind of like two things kind of fixed. So, and basically I'm gonna like show you this table in more detail, but there will be a signal coming from this that tells you whether we found this index or not. And if it says it found that, then that signal will be connected to this controller, right? If we didn't find that, it means that this either is not a branch at all, or if it's a branch, we haven't seen it before. So let's not think that this is taken. So let's continue with PC plus 4. Okay. So again, quick recap, a step back. We talked about missed penalty. We talked about moving the decode, everything to the decode stage, and we always not taken at that stage. We said that basically our missed penalty is one cycle, and our accuracy is 30% for branches. Say how we improve this. Say okay, let's actually instead of doing not taken, do taken, and immediately improve our branch prediction. Our miss rate from 70% miss rate to 30% miss rate, or our hit rate from 30% to 70%. The problem was that with this approach, we needed the next PC during the fetch state, and we also kind of need to find a clever way that knowing that this is indeed a branch instruction. The way we fixed that issue was adding this BTB, this table. And the thing that we did in order to fix the second issue was we only put things into our BTB when we are sure that this is a taken branch. Okay, so we're basically saying that, oh, if I find something in this table, it's guaranteed that this is a taken branch. So I don't need to do a controller. I don't need to decode. All I need to do is kind of compare. And if I see that these two elements match, it means that this is a branch.
then you have a example like node loops. Here code you have keep adding stuff.
Yes. So the question is, if you have an if then else that doesn't happen again and again, you just keep adding chunks to your BTB. Yes. There is no way that we know that this happens again or not, right? Again, there are solutions for that, which we're not going to go through in this class, but there are solutions for that too. But good question. Yeah. So the question is that what happens for those instructions we haven't seen before? We will predict them as not taken. And during the decode, we will see that this is actually indeed taken. So we pay that 1 cycle penalty. Yeah. That's the accuracy. So as I said, we're not going to get 100% accuracy, right? So, all right. And then the nice thing about this is that nothing bad happens for non-branch instructions. Why? Because there will be never a scenario that PC goes into our BTB, because remember, we only put branches that are taken. So our non-branches are good. Our seen before branches are also good. And the only problem is not seen branches, right? So we kind of like cover a lot of different scenarios in this system. So you might ask why this works, and because we talked a lot about this, and we also talked why are we, like, for example, using PC and what bits of PC should we use. And the reason that this works is 2 things. One, 2 kind of like, kind of features in our systems, in our programs, that we're going to use a lot in this course. When we are talking about caches and memory, you will see these 2 terms again. We call them locality, which means that there is some sort of correlations between instructions that are close to each other's, or either in locations wise, like, PC and next to whatever instruction that you have, or over time. So you will have what's called temporal and spatial locality. Okay, what it means is that the temporal locality says that if I do something, it's very likely that in future I'll do the same thing over and over again. As I told you, this is like generally the practice that we are using when we are writing our program. And if you go back into all the programs that we've written, you will see that it's actually what's happening over and over again. Doesn't mean that you always do that, but it says on average, as I said, 90% of the time, you are repeating something that you have done before. And this is backed by data. It's not something that I'm saying. It's actually something that people looked at many different programs and found this. Okay, so that's temporal locality. And spatial locality says that if I do something, it's very, very likely that I'm going to reach out to the instructions before or after, like very close to that. Okay, so this is basically what we call spatial locality. This will be very useful for data. So for example, if I access A0, 1 index in my 1 array, a random array, it's very, very likely that I'm going to use A1, A2, A3, and so on in future. Okay, and we usually call this data locality. And the trick that we're going to use in future, as we will see, is that whenever we're going to bring A0, it's a good idea to also bring A1 and A2 and A3, because we're going to use it in future anyway. Okay, we usually call that spatial locality. Okay, so and then I already talked about that. That's, it's actually, interestingly, both of these are very, very commonly used in our programs. And based off that, this is the way that we're going to use our BTB. So think about BTB as basically this array of lines, which each line is basically 1 target address per entry. And the way that we're going to index this table is, first of all, the first 2 bits we're not going to use, because our PC always increased by PC plus 4, so we don't need the first 2 bits. So we can just ignore the first 2 bits. We're gonna then use this index bits here to address this elements in our BTB. And the reason that we are using PC is because we're gonna, you can think about this as some form of temporal locality, because if you are in this PC and we store things based on this PC, very likely in future, we're going to come back to this PC and reuse it, right? So this is basically kind of a definition of temporal locality. And this index here is basically saying that I'm going to use this bits to kind of like, index these things. And this is kind of like spatial locality in some sense, because if I store these things, it's probably like I'm going to store something nearby in the next branch and next branch and next branch. Okay. And based off these two, basically that's the way that we're going to store these things into our BTB. And as I said, we're going to have a mux here that either gets PC +4 or gets this value from this PC, this address that we're storing. Another thing that we need to think about is, okay, a new PC comes in, and what I have here is just the address, right? How do I compare that this PC is indeed, exists in this table? So for that, we need this additional table called tag table, which kind of like, very basically, it can store the whole PC there. So we're going to say, for example, we are at 0x20, and then we have branch equal, and this branch equal jumps into this address, okay? And then maybe somewhere else at this 0x30, or 0x400 maybe, way down, we have another branch equal that jumps to another address 2, okay? Address 1, address 2. So what we will store in this tag, so in this BTB, what we are storing is address 1, and assume that both of these are taken branches. So address 1 and address 2, but in addition to address 1 and address 2, I need to store these two values, right? So what I do is I store 0x20 or 20 basically, and 400 here, okay? So we call these tags because this is basically tell us which branch is this, because the next time this branch comes in, I know that this is whether this is this branch, or something else, right? So I need to know this. And the first thing that we're going to do is that we're going to actually compare the tags with the new instruction. And if these two matches, then I'm going to use this instruction. So remember that mux that we talked about? This is actually the mux coming from comparing the tags with the address. Another trick that you're going to see is that the tag is not the entire address. The tag is only a portion of this address. And this is a minor optimization that we do, because we're saying that, you know what, I'm going to use this bits for indexing this BTB anyway, right? So if, for example, this tag is like, let's say you have something like 0x20, right? And then let's say I'm using 4 bits for indexing and 4 bits for tag. So 0, 0, 0, 0, 1, 0, 0, right? So this is the binary value of this. What I'm saying is that I don't need to store the entire 1 byte for 8 bits into my tag, because if I'm using this lower bits for indexing this table, 0, 0 means the first line, 0, 1 means the second line, 0, 2, 1, 0 is the third line, and so on and so forth. How many of these bits we are using? So this kind of implicitly goes into the right index. And I only need to store this, because index plus my tag becomes the entire PC. And then that way I can basically recover and recreate my PC. Okay. So alternative to this was, I'm going to use the index, but I'm going to store the whole thing. And for storing the whole thing, I'm kind of wasting this index, whatever that is. What I'm saying is that you are already using your index to addressing that table. And for each unique index, you are reading something unique from that table. So you don't need to store that index anymore. You already know which index is which. All you need to do is storing the rest of your data in that element, in that cell, and that would be what we call as tag. So basically your address, your PC, is combination of your tag plus the index, where the index is basically tells you which row is this, and the tag is the value that is stored there. And the reason that we are doing is that we are saving some bits to be stored in this. So our tag space significantly reduces. For example, in this case, I'm reducing the size of my tag table by half because I only store 4 bits compared to 8 bits. Is that clear why we're doing this? Any questions? The question is, are PCs guaranteed to be 32 bits? For our scenario, yes. If not, still the same. So if it's not 32 bits, then our tag basically becomes bigger, right? So our index stays the same because log2 of our index is the number of entries, right? Sorry, number of entries, log of number of entries is the number of bits that we're going to use in index. The rest, whatever it is, if it's 32 bits, it would be 32 minus index, that would be our tag. If this one is 64, then you need bigger tag. Does that make sense? And then the reason that we are doing -2 is, before answering your question, is because we are not using these 2 bits. Because remember, we are doing 4 bytes and everything is byte addressable. So we're not storing the first 2 bytes because it's always 0, 0. Okay? Yeah, sorry, go ahead. Yes, for RISC-V IN32, this is the value that we need to use. The question is, what is the difference between tag and index? So the difference is, let me do it one more time. So we have an input and address, which is the PC in this case. We're gonna get rid of the first 2 bits, of course, first of all, because that's the byte addressable thing. Then we're gonna divide our address into what we call an index and a tag. We're gonna use index in order to actually go through these elements in this table. So this is a table with multiple rows. So the first thing we need to do is going through one of those rows, right? The way that we decide which row to go to is using this bits here, using this index. The reason that this index is not the same, like, it's not 32, is usually we don't have 2 to the power of 32 entries in our table. If we had that, then our index would have been 32 bits. We didn't need a tag at all. What we do usually is much, much less than 32, because 2 to the power 32 is like megabytes of data. And we're not using megabytes of data just for BTB in our processor, okay? We're talking about kilobytes, which is basically like 10 bits, 20 bits, or something like that, okay? So there will be some part of the address which is going to be unused, and we call that tag. In order to recreate the whole thing, we're saying that, okay, this index is being used to access this. So for example, line 4 is 0, 1, 0, 0. Okay, so this is our index. So I don't need to store this. All I need to store is rest of the address. I'm going to concatenate these 2 together, and that will give us the final address that I want. So I'm basically, this is an optimization. All I'm doing is I'm not saving this part because I'm saying that whatever row this is, that's my index. That's all I need to know, right? So I'll just use that in order to recreate my address. Does that make sense? The question is that there is less entries in tag table than BTB table. No, there's same amount of entries. The width is different, right? So here you only need to store whatever this is, whatever this value is. Here you need to store 32 because that's your address, right? So you have same entries. This one is 32. This one is 32 minus index minus 2, whatever that number is. So for example, if you have 1,204 rows, it means 10 bits. So you have only 20 bits in here and 32 bits in here, but same entries. Does that make sense? Yeah. Yeah. Yes. Yeah. Yes. So the question is that when the new PC comes in, that address is divided into index and tag, and all those things will happen. Yes. But basically, that's again a wiring thing, right? So your PC is your register. What you do is that you're reading the first, so let's say 10 bits, and use that in order to address that. And then you take the rest of 32 minus 10 minus 2 bits as the tag, and then you're going to compare it with whatever value you read from here. There will be a comparison here. This comparison would be either 0 or 1. If it's 0, it means that I don't care about what address I'm storing here, because this is either not a branch or it's not a taken branch. So I'm going to ignore this. I'm going to pass this PC plus 4 to my next PC. If this is 1, then it is guaranteed that this is indeed a branch taken. So I'm going to use this address. I'm going to use this 1, and I'm going to do next PC equal to that address, whatever that is. Okay.
So should there be a or for what
So the question is, should be an OR case or an AND case. So basically, what happens here is that if there is no entry, the tags won't match, because at the beginning, think about that this table is full with zeros. Okay. So if a new PC comes in and we don't have that entry in our table, the index goes and grabs some garbage out. And that garbage won't match with our tag, because our PC is something and this tag is 0, 0, 0. So we are comparing garbage with a real tag. They won't match. So this would be 0, and we will get PC plus 4. The question is the garbage going to be always 0, 0, 0? Yes, we will. Usually the trick that we're going to use is that we're going to add another bit here called valid bit. And that valid bit is going to say that, oh, just ignore this garbage. It's garbage. Oh, you mean like, what if this is 0, 0, 0 and this is 0? True. So I mean, the question is, what if your tag is indeed 0, 0, 0? Yeah, that could happen. And again, for real systems, the operating system handles these things. Basically, it pre-populates the BTB with correct addresses. Usually, the first few addresses is reserved for the operating system. So the chances that this is indeed 0, 0, 0 and these two matches is not 0. It's 0. So basically, the operating system takes care of all these address translation for us. Once we get to the virtual addresses, we will see that how this is done. But that's good question.
Higher index, the PC as our index, and also the value in there, but
the question is, we could have just used the entire PC as our index. The problem with that was that you need 2 to the power of 32 entries, right? So you couldn't do that. We good? Yeah. So the question is it possible to have same index and the tag is different? Yeah, of course, right? All these, let's say your index is 0, 0, 0, 0. Everything here that has values that the last 4 bits or whatever n bits is 0, 0, 0, they all match to the same table, to the same entry. So they kind of compete for the same entry. And that's the problem with having less number of entries in your table. They kind of kick each other out, but nothing bad in terms of correctness, nothing bad happens. So there could be scenarios that we have seen a branch and we put that into our BTB. But before seeing this branch again, we see another branch that happens to have the same index as this one, but a different tag. What will happen is that this one goes and replaces this value here. So next time, if by chance we see this one, we go to our table, our BTB, and say that the tags don't match, and we think that this is a new branch, so we just do not take it. So this would be an accuracy problem. And the problem would be because we have limited number of entries in our BTB. Ideally, you want to have as big as possible BTB so that you won't have this, what we call conflicts. If you don't have this conflicts, then you're good to go. But there will be conflict like this. And the reason that I'm not going talking more about this is that once we talk about caches, we will revisit all these things and we will talk about conflict and misses and all those things. Same story here. Okay. Okay, so we talked about all these things. Let's kind of like, finish the discussion. So if you think about all the control flow instructions, we have a bunch of different types of control flow instruction. It's not just taking branches. We have what we call conditional branches, which is basically things like branch equal, branch less than, and so on. The direction of these branches is unknown. We don't know whether this branch is taken or not. But the good thing about them is that it's only two possibilities, right? Either it's taken or not taken. So there's two possible addresses for these conditional branches, right? Then we have unconditional branches. This is your, for example, your GL instruction, which always taken. So whenever you reach to the jump instruction, you never doubt that whether this is taken or not. It's always taken. And the nice thing is that it's always jumps into one address on only one address, right? So always taken and only one possibility. Then you have call and return. And if you remember, we said that call and returns are essentially jump instructions, the same jump instructions. So again, very similar to unconditional branches, always taken, and the address is one. The return, though, is slightly different because the return jumps to whatever RS, if you remember RA, which was X1, is pointing to. So if you're jumping this function from this point in your program and you run that function, you have to jump here. If you jump the same function here, you have to jump here, right? So your return has this many different possibilities for returning, right? And same story for indirect branches, because return was a special type of indirect branches. Generally, indirect branches, it says I'm going to look at RS1, and whatever RS1 is, I'm going to add offsets to it, and then I'm going to jump there. And since RS1 can technically be any value between 0 to 2 power of 31 minus 1, we are talking about many different possibilities, right? So we either have one target address or two target address or almost infinite number of target address. Our direction of the branch could be, most of the cases, always taken, but in some cases will be unknown for conditional branches. Sometimes it's taken and sometimes it's not taken, right? So let's see actually with this BTB and all these things that we have done so far, how many of these we have covered. So for first of all, for non-branches, for R-type, I-type, LW, SW, and all those things, we are good to go. Why? Because our PC won't match with BTB, right? So it's always not taken when we are good to go. For a large majority of our instructions, we don't have to be worried about anything, right? For GL, we also good because this is exactly what BTB would give us, right? Because GL is this always taken branch. And whenever we see GL in our decode, we're going to grab that and put it into our BTB. And next time you see the same GL, you see that, oh, I have seen this before, and that's great. So for GL, BTB is exactly designed to help us, right? For branch equal, we have this idea of taken, right? So if the branch equal is taken, we are good. If branch equal is not taken, then we are not good, right? So we don't have any idea what to do. We always predict that this might be taken, and then we use that, right? And then for return and call and Jalor, given that there are many different addresses, we don't put that into our BTB. Maybe we'll put that one time, but given that there are many different options, probably the outcome of BTB won't help us at all, okay? So what we do is that we typically don't update our BTB with these instructions because they might have many different return addresses, and BTB is not a good idea for these instructions, okay? So we kind of like solve most of our problems, but we need to still think about direction of our branch and maybe improve our BTB with directions, and then also do something with our return and Jalor and call, okay? So again, going back to our design, we said that from not taken to taken, we are improving from 30% to 70%. But the question that we always ask is, can we do better, right? So can we move this 70% to 90%? And to 100%, close to 100%. And that's the idea of what we call dynamic branch prediction, which we essentially say that, I mean, now we have all these mechanisms for finding the branch and finding the next address. Maybe we can use and expand that a little bit so that we can also, instead of saying, oh, this branch will be always taken, sometimes we say, oh, this branch is not taken. So when I see that branch in our BTB, instead of incorrectly predicting it as taken, maybe sometimes you see that, oh, the address is there, but I'm going to ignore that address and I'm going to predict that it's going to be not taken. Okay. So for that, we use the exact same thing that we did for BTB. We're going to use history, but we're going to use history in a slightly different way, because we're going to use history to kind of like make a better guess. For history, for BTB was kind of like always guaranteed, right? But for branch prediction, this is not guaranteed, because the dynamic behavior of a branch can change. Sometimes it could be all taken, sometimes it could be not taken. We can look at the history and say, oh, this branch tend to be taken more than not taken. So what we're going to do is that I'm going to predict that it's going to be taken, and hopefully that would be correct. For some other branches, I'm going to see that this branch is most of the time not taken, so I'm going to predict not taken for this one. But it's not guaranteed. Sometimes we are correct, and sometimes we are not correct, and it's slightly different with BTBs. Okay. And the question would be, okay, how do we actually keep track of this, and how do we history? I'm going to show this and then leave you and discuss this further in the next one. So the trick that we're going to use is that we're going to add this thing called branch history table. And this history table, think about it as a new set of columns that we add to our BTB, which basically just say that this branch is taken or not taken and make a decision based off that. Okay. I'm going to talk about the details of this in the next lecture, but we're going to use this trick to kind of like predict the dynamic behavior of the branch. And another thing that we're going to talk about next lecture is like a quick overview of your quiz, given that you have a quiz on next Tuesday. Okay. So if you have any questions, let me know. Okay.